This work project is together work with Professor Axel Brandenburg. Pardon, he will come as well. Yes,
Who?
we can wait. Another student.
Oh, I see. Okay.
So, I don't know if we can wait.
We will just
after.
continue and then.
So the outline, I will introduce the topic. After that, present some results, and I will say some words about future work as well. So, we know that the Sun possesses a large-scale magnetic field, and the large-scale transport properties are affected by the shear. So we can ask, dynamo action from the shear current and alpha effect can explain large-scale magnetic field generation? And we will try to answer on this simulation. So one of the aim is the answer. So what is the real aim? Is to use the test scalar method we share to obtain a turbulent transport coefficient, and how? By imposing a gradient of the passive scalar concentration and measuring the result concentration flux. I will explain more detailed later on this presentation. The model is the weakly compressible subsonic turbulence in the presence of the linear shear flow. The method, we use pencil code, three-dimensional pencil code, and test scalar method. This test scalar method is included in pencil code. The initial condition is that we have no rotation, no imposed magnetic field. We have a constant density. The velocity is equal to 0. The boundary condition in the x and y direction, we use periodic and shearing periodic boundary condition. So let's start. Because we use the shear case, our equation is the Navier-Stokes equation for the density rho, that means the continuity equation, and for the u, which is the velocity, that means the momentum equation. So we use these two equations, and we use the evolution equation for a passive scalar concentration per unit volume. This is C. So we have this equation for C. We can construct similar equation for the mean value of the passive scalar concentration, and the difference between them is the fluctuation. This is small s. So this must be small s because, thank you very much, because we have these two terms as well. And so impose that we have a passive scalar concentration, and the gradient of this scalar concentration, measure the mean, so this is our method, measure the mean flux of the concentration density, and assume the Fickian diffusion ansatz. That means that this mean flux of concentration can be expressed with a rank 2 tensor Kig and the gradient of the mean concentration. So if we write this ansatz, it's equal to...
Your blue is better, huh? Can you see that?
Pardon?
No.
Okay.
No?
No is better past.
Yes.
Yeah.
Yes.
And the gradient of the mean concentration. So, if we don't have the shell, if without the shell case, if we will express the turbulent diffusion coefficient, we have only one term, but I will talk later when I will show the formula. Now we assume that we have anisotropy. That means that this concentration vary with direction. If we choose, for example, case 1, we choose C bar equal to X, we choose one direction, and we can calculate the gradient on this direction. It's equal because dx divided by dx is 1. And we apply the Fickian ansatz. That means that this, which is equal to UIC, is equal to this kappa Ig, which is an anisotropic rank 2 tensor. So this has 9 components. I mean here. Multiplies this with the gradient of the C bar, which is this. This is a vector and this is a tensor. So the result will be this multiplies by this is K11. This multiplies by this is K21. And this multiplied by this case 1. So we can calculate these components. Case 2 means that we choose C bar equal to Y, and case 3 means C bar equal to Z. We choose the X, the Y, and Z direction, and with help of them we can calculate the another component as well. So we have all ingredients, all components for this Kij tensor. And we will use this in our simulations. So, if the system rotates, we have rotation. That means we have omega. Omega is the angular velocity, which is a pseudo vector. Kij is the rank 2 tensor, the turbulent diffusion tensor. Kt omega and omega, the second order term, are coefficient which are function of the fluid parameters. In the case of shear, we do similar things. WV is the vorticity, which is a pseudo vector as well, equal to rho u. U is the flow velocity, and we can write U as sum of the symmetric and antisymmetric term. The symmetric and antisymmetric term, the mean value is defined as their comma means derivative. And we can express the antisymmetric term with the help of the vorticity as well. So, we can write the rank 2 tensor with the help of coefficient t, kappa t, s, a, s, s, s in the rotating case, for the shear case. And here, if without shear, we have only these terms. With shear, we have another term because the turbulence is not isotropic, depends on the direction. And something, it was very hard to study this turbulent anisotropic case analytically, so the simulation is a very useful tool. We know these 9 components, and with help of them we can calculate the turbulent coefficients, which the number is 5. There we have 9. If somebody is interested, after the talk I can tell more about this. Sorry for this plot. Due to the lack of my time, this is not in log scale. With the help of log scale, we can see better how in the beginning it increased linearly and later became more stable. Sorry for that.
What are the different
Yes.
symbols?
So this is the shear parameter, and K1, 1, 2, 2, 3, C are the components on the diagonal. So this with
What are the different symbols?
pardon?
There's like black asterisk, red
Ah,
asterisk.
sorry, it was there, but I
Which one was 3, 3?
yes,
huh?
I had what I have deleted.
Mhm.
Yes, I can say you. It was on the slide. Yeah. But what is important that in the beginning they have similar value, and later on higher value
Smaller
their
values, 0.
yeah, it's minus. Smaller value, the difference between them became more
And SH
important,
is defined
more.
as, can never remember.
Pardon?
SH is defined as.
SH is the parameter. SH is equal to S divided by URM multiplied by KF. Yeah. So here I have log scale, so we can see better. Mu is the kinematic viscosity, and the same diagonal coefficients K1, 1, 2, 2, and 3, 3. We can see that in the beginning they are almost they have almost the same constant value,
Wait. Now,
almost.
I'm curious, what are you
That means, but later they decay linearly.
what are you normalizing this to? What are you normalizing kappa to?
here I don't normalize. I put only
You mean
as
you?
they.
Are you asking you maybe how you normalize it? Kappa you normalize with kappa T naught.
Later, but not
And
here.
also here.
Not here. Here I put S there.
Can you go back a slide then?
Hmm?
Can you go back a slide? So you're varying SH. How are you varying SH?
I put SH was S was equal to 0.05. And here we have different values. So in that case we put
What did you vary
different.
the simulation?
And you can see the value.
Yes. How did you vary SH?
Pardon?
How did you vary SH?
She said already with S.
I said S divided by URM multiplied by KF. So this is.
So you're saying you're holding S constant.
No. S varies.
S vary. And if I vary S, SH vary as well.
Okay, you're varying S.
Yeah. Okay. So here I normalize. KXX means 1, 1, 2, 2, 3, 3. Here is normalized to K naught, 0, which is equal to URM divided by KF. And so here we use log scale. The PE is defined like URMS divided by kappa KF. And kappa is the microscopic diffusivity. Yeah. Questions? So they behave similar. So before I talk about the turbulent diffusion tensor expressed with the help of turbulent transport turbulent coefficient, which are KT, S, SS, A. And here we express this coefficient with the help of Henkel number. And what is a very important result, that K behave almost like PE squared.
For small.
Almost. For
For small.
small Henkel number. That means much less than 1. So this is the K result, a very important result. We have KT, S, SS, AS coefficient normalized to KT naught and as a function of the PE, and we can see that they behave, so we have a log scale, and they behave here they increase, and as I said, like squared, P squared.
How are you defining KT naught in this case?
Pardon?
How are you defining KT naught in this case?
KT naught is URMS divided by K. This.
And 1/3.
Pardon?
1/3.
And the value of
No, divided by 3 also.
yes, by 3.
Sorry,
Third, yes.
I was thinking your x-axis is one different, so go on.
Okay. So another result, here we have the same coefficient normalized, as a function of the wave number normalized to K1, where K1 is the smallest K number, that means 1 divided by the box size. And we can see how they behave. Decrease or here decrease and saturate. So this is another result. Here we have K112233C normalized as a function of the wave number normalized to the smallest wave number. And we see that K11 and 22 behave the size. Their size is almost the same, but K33 has smallest. The size of K33 is smaller than the other two, K11 and K22.
And
The
we are
reason
now-
why, I don't know.
We are now working in case 1, or we are working in all cases. Which case do you represent?
Pardon? So this K11 this value. So we are interested only on the diagonal.
I'm pretty sure, are we actually using those gradients?
Components.
Are you using those?
No, then you have cosines.
Okay.
In that case, you have sines and cosines. Yes.
So we're using all three to calculate all the values. And the concentrations are actually sinusoidal.
Thank you. Yeah. And something I would like to finish that I ignored a lot of things because today we have a lot of presentation, seminars, so I try to present a shorter variant of the talk. And this is only the beginning. We have a lot to do. For example, we are interested to see the long time running behavior or detailed study of the mean turbulent concentration flux, share the connection between shear and gravity, and so on. And thank you for your attention.
Thank you. Yes, questions, please. Or further questions, please.
What's the conclusion of the talk?
Hmm?
What is the conclusion of the talk?
The conclusion, I said that this is only the beginning. The main conclusion was that this K1122 how they behave as a function of the wave number, the amplitude number, and another conclusion was that the diffusion coefficient vary as Painter number squared. So we expressed them with the help of the Painter number.
So the behavior of the three.
Yes. So this.
That's the conclusion.
And maybe go back to the other plot here, previous one further. Yes.
Both sides.
Oh yes, and even that previous one, first of all. I just
This?
was looking during your talk. No, the previous one.
Oh.
Twice previous. Next one again, forward.
Yes. What is this?
No. Here. I realized there was this was this cubed, and this was the fourth power, and this I think also to the fourth power. So that means, as one sees also from these plots, they come all in this higher. So this goes in quadratic, and these come in with higher orders, third power and fourth power. So, and it's those effects which determine the imbalance on the diagonal. So these must be higher order effects. You see that directly from the scaling of this Peckley number. So this can then likely not be understood using first order smoothing theory, the fact that this, for example, is different from that.
And the problem is the fact that K22 is different can be understood.
That can be understood.
Yeah.
Yeah.
Sure, and you're
Yeah.
getting K11 until the K22. So it's like, even there's
Yeah. The difference I think are always very small between the.
difference is not small, it's large, it's a factor 50%.
Is this tumor axis?
You mean here, yeah?
Yeah,
Yeah.
factor 2.
Well, high. Yeah, here it looks rather dramatic. I'm also a bit surprised. I mean, normally it's this one which is bigger than the others, as we also saw from this other plot. Which one was it now? Yeah, here. And here, if you look at this again, here you don't see much of a difference except here. And then even then it's not so clear because of error bars, of course. Now, we'll actually discuss whether it makes sense to do this split in terms of.
I mean, you can do that in terms of symmetric and
Yes.
antisymmetric. It just feels to me like you still need an explanation for why kappa 11 was big in that plot. And I still have no idea what that is.
Yeah, but I mean, the fact that it can happen is plausible because if you construct this kappa tensor using the building elements, as she said, S, A, S squared, and SA, then you can construct these orders. So
Yeah.
this, for example, is you've verified this.
Like that's, yeah, that's
Yes.
yes.
And then this one is this, and this one is this one.
Yes.
So with those construction elements for the tensor, you can.
You can generate
Yeah.
things like they're different, they're just.
And the experimental result is that those effects come in at higher order, at the fourth order. And so with the simple tau approximation, unlike what I was saying over lunch, one cannot get this difference.
And you use the same error bars as we did.
I think no, that's indeed an open question. I think we were very confused about error bars.
It averaged first on the Z direction and after that for different spatial time and use the standard deviation. So this is a complex.
Can you go back a bunch of slides to the one with the colors that I put up before?
Plot.
Yeah, that one right there. So what here is URMS, sorry, UX RMS times S times tau divided by URMS.
So what is that?
What? UX RMS times S times tau divided by URMS. Because I'm wondering if your URMS is getting dominated by shear.
No, it doesn't. Because the URMS is defined in terms of UX and UZ only.
Okay.
The Y is not taken into account. For exactly that reason, yeah.
And why on earth is your kappa 33 dependent on your SH? How does that happen?
I'm not sure about those data, but at what time was that? Was that at the late time when the vortices dynamo took over, or was it at early times still?
I
Maybe
think
it's
that it
early
was
times, yeah.
early time.
Yeah.
I think.
Yeah, no, but I mean, what's the problem there? I mean, clearly enough.
The shear's having absolutely no effect in the C direction. Or it's very hard to get the shear to have any effect in the C direction. And yet your kappa 33 is depending extremely strongly on the shear.
Yes, and also for components.
All components, but especially the fact that kappa 33 is depending on the shear is bizarre because the shear is in XY plane.
Okay, I I will check.
I mean, I can sort of maybe imagine the shear generating weird pressure effects,
Yeah.
but thereby boosting UZ. But that would boost UZ, so that would boost kappa, not decrease it.
Mm. Yeah, maybe this these I think these are very early results on this plot. So I don't think there could indeed be a problem with normalization, unlike the other plots that we did later. So that I would not be too sure about this. I don't know too much about this. We were doing SH dependencies at fairly low resolutions initially, and then later on we went to factor number dependence for one variable S only. And only then we elaborate on the analysis tool used for example UX and UZ. So that could be all kinds of other things.
And how did you scan Pecklin? What did you vary when you're scanning Pecklin number?
U,
Yeah.
which is equal to Eden. Okay. Yes. Any other questions? So, okay, Fabio is still ill. Yeah, but then I think Nico gets again. And next time will be